Good morning. Starting to feel the end coming soon. Not to the world. I feel like it could be but to the semester. Oh, we got like 2.5 weeks left. It's kind of crazy. Well, at least I have no like depressing stories to start off our class today. Feeling fine. Okay. How are projects going, by the way? Have you really had any time to work on this outside of the outline? Also, we are missing a lot of people for 10:59. A few more people. Whole 5 units. Well, hopefully when doing this daily homework, this didn't feel too bad. I think quotient groups are a little more challenging, but products are like pretty nice because things are just, you have more than one group, but like since it's all independent in terms of the coordinates, you're basically just dealing with one group at a time, and so it's kind of just stuff you've already been doing for the most part. And when we talk about orders of elements, we'll see that like our work with the symmetric group and thinking of disjoint cycles is actually like very similar. And so a lot of this stuff should be hopefully pretty intuitive for products. Okay, so see the number creeping up. So let's go ahead and get started. Um, yeah, so we're going to talk about direct products today. So very much like switching gears for a second here from normal subgroups. So the back half of this chapter is on quotient groups, and that will be using cosets and normal subgroups a lot. It's going to be defined in terms of those things. But for direct products, the definition and stuff is fairly straightforward, right? So if you haven't seen a Cartesian product of sets before, well, you may not have heard that name, but you really have because you've dealt with things like R3 or Rn in general in like linear algebra and stuff. And so, if you see a G cross H, then you're just viewing this as all pairs where your first coordinate has an element from G and your second coordinate has an element from H, right? And so like R3 you can think of as R cross R cross R. And so this would just be like an ordered triple, right? It's going to be like an A, B, C or an X, Y, Z. Pick your end of the alphabet that you like the most, where all of these guys are real numbers, right? And so this notion can be extended, obviously, like I did it for 2, I did it for 3, you can do it in general. So if you see the product of in things, you'll often see this, right? So remember, if you saw like x1 down to xn, you'd use your sigma notation, right? You'd say like the sum from I equals 1 to n of xi. Well, we have a same thing there, so instead of a capital sigma, we use a capital pi. And so this would be like the product from I equals 1 to n of our gi. That way we don't always have to do the dot 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 stuff, but like you definitely can. You know, there's no meaning that's lost there, but sometimes it can be useful to have the nice little shorthand notation. So yeah, that's what a Cartesian product is. And then, you know, to actually make it the direct product, we have to give it a group structure, right? So that was what you were doing in 6.1. So if G and H are groups, then G cross H is a group where the multiplication, right, where the operation is, you know, you take two things, say G1, H1, and you have star G2, H2. This is just going to be G1, G2, H1, H2. And now I'm leaving off some of the notation that you see in the book there because, well, you'll basically never see it. People aren't going to use stars and like circle dots and stuff. But the key thing to note here, right, is that these are with the respective operations from G and H, right? So like that multiplication could be different if these groups have different multiplications with the respective operations from G and H. Right, so you could have, for example, something like D3 cross Z3, right? And so over here, you've got your like function composition, and here you've got your like addition mod 3, right? And so when you compose things, you know, if you have, for instance, let's just say R1 star, let's just say R2, then what do we get? Well, you get the composition over here, so you'd get R squared, and then you'd have like 1 plus 2, which is 0, mod 3, right? So this would be like R squared 0, for example. Okay, so just remember to do like the right operation in each one, right? So you're viewing it in each coordinate, and so just think about the operation with the single group you're dealing with at that time. Okay. Okay, so why is this a group in general? Well, we need a few things, right? So we would like to have an identity. Well, I mean, all right, yeah, we should probably even check axiom 0 here, right? So that this is really a binary operation so that we actually get closure. Well, yeah, we're going to, right, because each one is closed individually, right? So G and H are closed. So if, you know, G1 and G2 are in G, and H1 and H2 are in H, then when you take the product, right, you're going to get something in G and then something in H. So it's closed. Yep, we're good. Associativity follows similarly. Yes, similar follows from G and H being associative. What's the identity here? What's our identity element in the product? And if you want to hit me with both, since we've got the little delay, what's the inverse? So GH inverse equals blank, and then my identity equals, yeah, e to the 1. What do you mean by e to the 1? Or is that just like the other identity? Yeah, so I mean, I would say, you know, maybe like E sub G, so it depends on how you write it, right? If you want G1 cross G2, then it'd be like, yeah, E1, E2. Yeah, okay, other identity, good, yeah. And here, you know, maybe I call them EG and EH for the identity in G and the identity in H. Yeah, and since multiplication is just, you know, multiplication in a coordinate at a time, then, well, this is going to be the identity. So what's my inverse for an element? Yep, exactly. Yeah, so we just get G inverse H inverse, right? And then it's pretty easy to check that, right? So GH times G inverse H inverse is equal to, well, that's the identity and that's the other identity. And so we're good. And so we get a group, and now we're ready to like talk about what properties does this have, right? So some things you had to find out was that, you know, the product is abelian if and only if the factors are abelian. And by the way, yeah, I would call like G and H the factors here. You know, we will learn about like the orders of elements in these, or just, you know, the order of the whole group itself. And these things all follow like pretty quickly. So first, let's just kind of look at this example that you guys were given, right? So it was Z4 cross Z2. Just want to make sure I had the right factors in each. So, right, your left coordinate, the way I list these out is I just kind of fix one at a time, right? So, you know, your left coordinate can range from 0 to 3, and so I just do all the ones with 0. Whoops. So like 1, 0, 2, 0, 3, 0. And then your y coordinate there, your z2 coordinate can also be 1, and you just list them all again, right? So we've got 8 elements here, which, you know, kind of matches our intuition, right? We have 4 choices in one, 2 choices in the other. They're independent, so it should just be the product, and it is. So let's just play around with a couple of things. So if we wanted to find the inverse of, say, 1, 1. So now remember, our operation here is addition, right? So we're looking for the thing, we're looking for AB such that AB plus 1, 1 equals 0, 0, right? And I mean, we can just look, right? A inverse is going to be 3, because 1 plus 3 is 4, which is 0 in Z4. And then, well, 1 is its own inverse in Z2 because it's the only non-trivial element, right? So our inverse here is going to be 3, 1, right? Yeah, good. Right. And in general, right, we're just like adding things. So if you just wanted to like add random stuff, you know, let's just say we had something like this, and you see these 3 elements. What are we going to end up with here? Yep, 2, 0, right? So the first coordinates add up to 6, the second ones add up to 2, but in our group, that is 2, 0. Good. Okay. So yeah, that's just some basic practice we want to get used to. So we wanted to figure out, you know, what's true about this group. So it's a product of 2 abelian groups. It's also the product of 2 cyclic groups, right? So some natural questions you may ask is Z4 cross Z2 cyclic first, right? You'd just be like, okay, it's a product of cyclic groups. Must it also be cyclic? What do we think? And you could use the Cayley graph or not, right? You can just look at the elements as well and see what you think happens. Right. Yeah, it's not cyclic. One way to think of this, so remember back when we talked about S4 not having any elements of like order 8, right? We looked at like the cycle type and stuff. And like the issue, right, was that like the length of the cycle could be no greater than 4, and like no matter what you did with the LCM, you were kind of screwed. Well, think about it here, right? Like nothing, like anything to the 4th power, or I guess 4 times anything since we're doing addition, is going to be 0 in both, right? So like 4 seems like the maximal order you could get here, because no matter what, when you do something twice, you're the identity over here. When you do something 4 times, you're the identity over here. And so if you do something 4 times, well, that's doing it twice. So it's going to be the identity in both, right? So can't get over order 4. And there is an order 4 element, right? So 1, 0 is order 4 here. For abelian, theorem 6.5 gives it. Yeah, true. Yep. So it is abelian. And this shouldn't be too surprising, right? That is all about, like, again, the factors are independent of one another. So if each of them are abelian, then how are you suddenly going to get things not commuting if you're not mixing factors, right? And so that's the basic idea there. So I mean, we'll prove that rigorously here in a bit, but yeah, that will do the trick. So then the last thing was to determine, okay, is this an order 8 group we have seen before, right? So we've seen order 8 groups. So we've seen D4, we've seen the quaternions, we've seen the cyclic group of order 8, and we've also seen L3, right, that light switch group. Ah, is it the same, Tyler? You have to look closely. It looks an awful lot like it, but there's one difference. Because also think about this, right? If they are isomorphic, could this be abelian? Right, because D4 is not abelian. So if you look at that Cayley graph, the key difference here, yep, the arrow direction is different on the inside. So D4 has the arrows going the opposite direction on the inside that they did on the outside, and this one has them going the same direction. So yeah, they look super similar, but it is a little bit different. Oh yeah, no need to apologize. Right, so nope, it's not D4. It's also not going to be Q8, right, because it's not abelian, right? Both not abelian. And we've also shown it's not Z8 because not cyclic. Well, this one's cyclic, while our group is not. What about L3? So, I mean, that one's not cyclic, and it is abelian. Is it the same? No, and exactly, that was actually going to be my follow-up question was, can we write this as some product? So yeah, no, and the reason here is 1, 0 is order 4 in Z4 cross Z2, but nothing in L3 has order greater than 2. Right, because it's the light switch stuff. So like you're either on or off, and like you either do it or you undo it. Everything was its own inverse except for, well, I guess that's just true, but then the identity would be order 1, everything else is order 2. And yeah, as Tyler said, L3 is actually isomorphic to Z2 cross Z2 cross Z2. right? Where you're basically just saying like the on and the off, you're just equating with 1 or 0 in each coordinate, right? And you've got your 3 light switches. So yeah, that's really cool. And now, so that's something that like we didn't have these cyclic groups yet, and so I introduced it as like this light switch group, but like this is the way you would usually see it, right? Just like we said, all cyclic groups can be written as like Z or Zn, depending on if it's infinite or finite. You know, you would never really see the light switch group written L3 in the out in the real world, if you will. You would always see like Z2 cross Z2 cross Z2. Okay. So the next ones, I don't think we need to like prove all of these, but it's probably useful to see why, you know, G1 cross G2 is isomorphic to G2 cross G1. So you just kind of have to figure out a map, right? And it's pretty obvious what it's going to be. So you would want to define phi of the pair G1, G2. And by the way, I'll usually just do this one set of parentheses as opposed to like phi of this, just because it's kind of understood. It's just kind of like a notational thing that's pretty common just to avoid cluttering with a whole bunch of parentheses. And you just flip the order, right? And then you just have to check stuff. So is this an iso, right? So the homomorphic property, well, if you've got phi of, say, G1, G2 times H1, H2, so here I will because I need to. I have two different things. Well, this is just phi of G1, G2, H1, H2, which is H1, H2, G1, G2, you just flip them there, and then you can drag it back, right? So this is H1, G1 times H2, G2, and there you can break it into your phis. So phi of H1, G1, yeah, G1, H1, geez, phi of G2, H2. And so it's homomorphic, and one-to-one and onto should be really, really clear, right? Because these are basically the identity in each coordinate. It's just that you've flipped them, right? So anything in G2 cross G1, well, what maps to it? Well, flip the coordinates, right? If you start with G2, G1, this is phi of G1, G2. So you know immediately, and then one-to-one, right? So if these two things are equal, then you would get that G2, G1 equals H2, H1, but this just means that G1 equals H1 and G2 equals H2. So G1, G2 is the same as H1, H2. Right, so it's fairly straightforward. So that's an isomorphism, and the next map is what you can almost think of as a projection, right? So if you think back to linear algebra, right, and you'd take like an x, y, and then like your projection map would send it to like the x coordinate, right? So you'd be mapping to, you know, x0 here, right? This would be the same thing. This would be kind of akin to the map from G1 cross G2 to G1 cross the identity in the second group by sending, you know, little G1, G2 to G1, E2. Open parentheses there. Right, so like this is something you've seen before. So this is called, you know, this is a projection onto G1. Now, kind of. So it depends on whether, so projection, I mean, you can either think of it as just completely eradicating this, in which case you just send it to the element G1 and you don't send it to G1 cross E2. Then it's not going to be an isomorphism anymore. Then it's just going to be, well, yeah, I mean, this is going to be an onto map. So the key is that these are the same, right? Like whether you keep track of that last coordinate or not doesn't really matter, right? Like this 0 would be true for all things along this, and so like you don't really need that piece of information, right? You just kind of know it's 0. So like the real information is being tracked in the first coordinate, and so that's why you have that G1 is isomorphic to G1 cross E2, and G2 is isomorphic to E1 cross G2, right? And so like your map, say in this first example, would just be, well, where does G go? Or even we can say G1. G1 would map to just G1 E2. And the whole point is like the E2 is not giving you any new information, and so like you don't have to end up worrying about it not being 1-to-1 or something like that. Or not onto. Okay, so yeah, these are also isomorphisms. I don't think we really need to necessarily check these unless you really want to see it. And then I'm definitely willing to go through it. But yeah, just let me know. So these are also isomorphisms. Maybe check it. Okay. Right. So 6-5 was essentially the same thing. So I didn't have you prove this, but basically that the n-fold product is also a group with the same idea for its operation, right? You just do the operation in each coordinate. Do the operation for GI in coordinate I. Right, and the fact that they're independent makes sure that like nothing is going to go wrong. Your inverse is the same thing, right? You just take the inverse of the element in each coordinate. Your identity is identity in each coordinate. So like all of those things just kind of follow the same way. So then a nice thing to know, and we've kind of, you could probably guess it from that previous example with like Z4 cross Z2, is that the order of this, right? So the order of this product is equal to the product of the orders if all of these guys are finite, if all GI are finite. Right, so if you've got like, I don't know, Z2 cross D3 cross S4 cross Q8, and you see this and you want to know how big is it? Well, all these are finite groups, right? And so you just look at it and you're just like, okay, this has 2, this has 6, this has 24, and this has 8. And so this is going to be the order, whatever that ends up being. I don't know. But like, why is this true? Well, you can just think of it in terms of like, ways you can have things occur, right? These are independent events, basically, like an element being in here, right? You have like 2 options over here, and those options are independent from your options in the other 3 coordinates. And so, for each, like for 0 or for 1, all of the options for the other 3 coordinates get counted up. And so this is why it's multiplicative, right? You want to think, if you've seen any like probability or statistics, right? These are like independent events, basically. And so it's multiplicative. And so you're really just counting up the number of options you have in each coordinate and multiplying them out. So that's how you get the order. And so obviously I had a condition here, right? Said if they're all finite. Well, of course they don't have to all be finite, right? So I mean, you could easily have the case of just like Z2 cross Z, for instance. So one way you can think of this, by the way, is if you had you know, we had like the light switches, and you had like a bunch of Z2s. So this is a little bit different, but you can basically think of like at each thing, if you had infinitely many things, so you're just like walking across like an infinite street of lamps, and you just kind of looked and you checked to your left, and you just see like, is this off or is this on, right? That would be how you would see like a Z2 cross Z, where your first coordinate is like on or off, and your second coordinate would be which of the infinite street lamps you're at, right? It's just kind of like numbering them in each direction. So like that's one way to think of it. Does G cross H cross F equal H? So it does not equal it, but it is isomorphic to it. Right, so your question was G cross H cross F, it's not equal to H cross G cross F. Well, I should be clear. If G and H are different groups. If they're the same group, then yes. But they are isomorphic. And basically your map there, right, would be like GHF goes to HGF. It's basically the same as 6.3, except for you have this last coordinate that stays there and hangs around and does nothing because you didn't change anything in your third coordinate. Yeah. So, yeah, with this group here, right? So, I mean, you have two options on the left, but you have infinitely many options on the right. And so it doesn't matter that one of them was finite. You're going to end up with infinitely many options overall, right? If you have infinitely many options in one coordinate, you're definitely going to have infinitely many options when you factor in all of the coordinates. And so if one of the GI is infinite, only need one. Actually, I should restate this and say one of the GI is infinite if and only if the order of the product is infinite. Because it works both ways, right? So if you have one infinite thing, then the whole product is going to be infinite. On the other hand, if the whole product is infinite, well, they couldn't all be finite, right? Because, well, we have a formula right up above for if they're all finite. You get a finite number out. And so at least one of them had to have been infinite. And so there you go. Right, so this direction, I mean, yeah, infinitely many choices in one coordinate. So infinitely many in all. And then this way, you'd say like, if all GI were finite, then what, that's 6, 6? Then 6, 6 says that the product is finite. So if you're infinite, then at least one of them had to be. Okay, so that's the contrapositive there, right? And the contrapositive is often useful when you're talking about like the whole product, because it's often hard to go from know something about the whole thing, then something about a single coordinate. Instead, it's easier to say like, okay, what if that wasn't true in this coordinate? Would that mean it's not true in the whole product? Okay, so like that's actually very common to see that direction be phrased in the contrapositive. I think that might be useful for this abelian proof as well. So this one, right, you guys were supposed to come up with here. So we had this theorem, which again seems to make sense, and like, well, we saw it in the one example we had with abelian groups. So if we have a bunch of groups, then the product is abelian if and only if each GI is abelian. What if you take the product of infinitely many infinite groups? What do you mean? I mean, like that's definitely allowed. It's going to be very infinite. But yeah, that's perfectly fine. You can have an infinite product of infinite groups for sure. There's no limitation. Now your cardinality can change in terms of like what type of infinity you're talking about. But yeah, no. Otherwise, like it still makes sense and it's definitely infinite. Okay. So, yeah, because we haven't talked that much about cardinality, but like it's actually really cool. So even if you take just Z2, this is maybe a little side note that I don't know if I should even make, but like why not? So the product over all natural numbers. So if you just did like the product from I equals 1 to infinity of Z2, this is going to be an uncountable group. Because you can think of this as like infinite binary strings, and you can basically get any real number decimal, right, between 0 and 1 like this, and the interval from 0 to 1 in R is an uncountable set. Basically, you couldn't just number them off and say like this one, then this one, then this one, right? Like 1, 2, 3, 4. That's what it means to be countable. So like that's pretty crazy. Yeah. So you can take even things of just 2 elements infinitely many times and suddenly get an uncountable set from a countable product. So yeah, cardinality is weird, but really cool. Okay. So kind of what I was saying before, right? So on this previous problem, that the one direction, which I've kind of written it the other way here. So this direction should be like straightforward. It should be direct. So here we can do just do it, right? And I will in a second. But then this way, it's actually easier to do the contrapositive because if you know this is abelian, you can do both. Yeah, that's fine. All right. Yeah, no, we'll do it direct. I think it's easier sometimes to do with the contrapositive, but we can do direct. So we'll show it. And if you want, we can even do it both ways. But okay, so if GI is abelian for all I, then basically GI abelian implies that little gi hi is equal to little hi gi if these guys are both in GI, right? And this is true for all I. So if you have 2 arbitrary elements in your product, right, and you multiply them, let me erase this because I may need more room, right? So this is going to be equal to, well, G1H1 down to GNHN, but then in each coordinate it's abelian, and so you can flip all of the orders. So this is where you're using since GI is abelian. And then you can just pull that out as the product. Right? And so we're good. We started with 2 arbitrary elements, boom, boom, and we flip their orders. I guess that looks cooler. Nice. All right. So what about the other way? So here we know the product is abelian. So I mean, the natural way for me is kind of the contrapositive. It seems easier because you don't have to like choose. So basically there you could just say, so if you did by contrapositive, this would be just if in some coordinate, right, if some gi is not abelian, there exists gi and hi such that gi hi is not equal to hi gi. And then all you would have to do is like not really worry about your other coordinates, right? So then any product where you have, say, shoot, the easiest thing in the world is just to do e in each coordinate, right? So let's just say we have like e1 down to whatever, then we've got gi, and then you've got all e's after, times all e's hi, all e's. Well, this is going to be equal to gi hi, which is not equal to hi gi, or yeah, sorry, equal to the e's in each coordinate, and then gi hi, sorry, down to en. But then this would not be equal to all e's hi gi by our assumption, which would be flipping the direction. Okay, so basically I just like picked out two elements I know they have to exist that do not commute, and then I just focus only on that coordinate, right? So there I'm basically using the identity because I can say like, okay, if I ignore all the other coordinates, like I'm really focusing on this one, that is basically just like the other ones are constant, might as well choose the identity, right? That's the thing that's easiest to multiply. So you could do it directly as well by kind of picking out this same thing, right? So directly, you could do the same thing. So for any gi and hi in gi, we would have this product, right? The order wouldn't matter. Equals flip them if the whole group was abelian, which would imply then that gi hi equals hi gi. And since they were arbitrary in an arbitrary coordinate, you'd be good. But basically, like both of the arguments rely on this same thing. And for me, picking out one element from this, like, I don't know, this feels less natural to me if I'm not doing it by contrapositive, actually. But you know, your mileage may vary on that. So whatever feels more natural to you, go for it. But either way, right, you just kind of have to make some choice on which element of the product you actually want to use to pick out this coordinate. And I recommend using the identity in every other coordinate just to make your life easy. Okay. All right. So what do we think about Z2 cross Z3? So we noted that Z2 cross Z4 had a Cayley graph that looked an awful lot like a dihedral group. This one should also look an awful lot like a dihedral group. Did you find that to be true? What kind of shape did you get for the Cayley graph here? So our generating set, right, was 1, 0, and 0, 1. It's kind of the standard generating set for these kinds of things. Yeah, it is like D3, and specifically, yeah, not the hexagonal one, because we're not generated by two ordered 2 elements, but the triangle within a triangle. I should probably make this a little bigger for my writing. So, you know, you can start on the inside, you can start on the outside. It doesn't really matter. I'm just going to start on the outside with my identity. So this guy, so, you know, I can make this more colorful. So I'm going to go down here, get this, 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 and then this, and this. And so if I have my 0, 1 guy from here, right, I can go here, 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 and then it's going to be the same on the inside. Again, this is the difference between this and D3 is these go the same direction. And then this guy will be my 1, 0. It's order 2, so I've got my two-way arrows, and you end up getting this, right? So 0, 1, 0, 2, 1, 0, 1, 1, 1, 2. Okay, so same questions as last. Well, we know it's abelian now, but is this one cyclic? Right, so Z2 cross Z4 was not cyclic. Should this be any different? Yes, it is different. What generates it? Yep, awesome. And the key here is we will find out is this is all about the fact that 2 and 3 are relatively prime, right? They have GCD 1, because basically you're not going to be able to get the identity in both coordinates until you have, again, the least common multiple. And if the GCD is 1, then that's going to straight up be the product of the numbers. And so you're going to get an element of order 6 here, right? So if you check like 1, 1, then you add it again and you get 0, 2, you get 1, 0, you get 0, 1, you get 1, 2, and then you finally finish up at 0, 0. And so you get all 6 elements. So yeah, like the Cayley graph looks like it maybe shouldn't be cyclic, but that's also because we chose two things that are not cyclic generators. So it's not easy to see what 1, 1 is doing. But if you made a green arrow equal to, like if green equals blue and then red, and you follow that 6 times, you're going to end up where you want. So you start here, and then you do blue, red, and then you do blue, red, and then you do, blue, red, and then you do blue, red, and then you do blue, red, and you finally get back to 0, 0. Yeah, so I mean, the Cayley graph is very dependent on your generating set. So I mean, if I had done just 1, 1 as my generating set, then I would have just gotten a hexagon. So it would just be this Cayley graph. And the order would have been exactly what you saw here. So like 0, 0 would have gone to 1, 1, 0, 2, 1, 0, 0, 1, 1, 2. Yeah, exactly. And the key there is that the GCD of 2 and 3 is 1. Yeah. Yeah, so we're gonna prove that here in 612. That's gonna be where we see the least common multiple is the key, and then it'll follow from that when they're cyclic. So, okay, I want to see. So you guys recognized earlier, right, that L3 should be Z2 cross Z2 cross Z2. So if you see just 2 of them, what common things that we have seen is this isomorphic to? Thing or things? Okay, yeah, so the obvious one is going to be L2, given the context that we noted before. But what was L2 isomorphic to that we've like talked about even more? And given your project choice, you should especially be familiar with this one. Yeah, it's V4. Think about it, right? So this is order 4, and all things are order 2, right? So you've got 0, 0, you've got 1, 0, which is order 2, you've got 0, 1, which is order 2, and you've got 1, 1, which is order 2, right? So it's 1, 2, 2, 2. And then V4 is the same, right? So it's like E, call this one V, it doesn't matter, H, and then this would be like your VH. And so this is the way to see that isomorphism. And you could just check, right, that this gives you like a nice matching. And you can just kind of see that it's true, right? That V plus H, or sorry, this plus this is like V times H, and you get 1, 1, you get VH. And so like, yeah, it's basically an isomorphism by inspection there. And so we also know what the Cayley graph looks like, right? So I mean, that one's going to be, right, say this is 1, 0, this is 0, 1, then you're going to get a square. Right. Okay. So the last thing I want to kind of talk about here, so I think the Cayley graphs can be somewhat helpful, just kind of getting used to this, but the thing we've kind of been hinting at for a little bit now is that if you have an element, I'm just going to call it G, in the product of the GIs, then the order of G is equal to the LCM of the orders of all of these pieces in its coordinates. So this is obviously where we'll assume that the order of GI is less than infinite. So it's finite order in all of these. Otherwise, I mean, it's just going to be an infinite order element, similar to what we saw with like 6, 6, and 6, 7. So this I'm going to have you try to prove. So I want you, my hint here is to look back at the proof for the order of sigma, where sigma was a permutation, right? So sigma and Sn, where this was the LCM of the orders of the disjoint cycles, right? Because it's pretty similar. I mean, this is the stuff that makes up sigma. All of them are independent because they were disjoint cycles here, right? These are the things that make up G. All of them are independent because they're in different coordinates. Like the idea is very, very similar here. So when you're looking at this, I recommend taking a look back at what we did on the previous one and see if you can like replicate that process and actually like prove this rigorously. Okay, so like this is the intuition. We kind of understand like why it should be true. It's got to end up as the identity in each coordinate. And so you've got to hit like some multiple of each of the orders. Like, can we make this rigorous? Okay. All right. So yeah, that'll be cool. And then you'll have just like a lot of computational stuff as well. So that's one of the nice things about these products of cyclic groups is you're often trying to find out about the orders of things or the orders of subgroups or the orders of the whole group. And it's useful to just get practice dealing with these and the LCMs. And then we'll kind of lead into a big structure theorem before we move on to quotients. Okay. So, all right, that's all I've got. So have an excellent Wednesday.